and welcome to CERN, welcome to the European Organization for Nuclear Research, the largest research laboratory in the world. My name is Jochen Jens Heinrich, I'm a research scientist at the University of Oregon. Here at CERN, we're home to more than 15,000 scientists from all over the world, including a small group of students and researchers from the University of Oregon.
My name is Tim Matthew. I'm a fourth-year graduate student at the University of Oregon. Here at CERN, there are several particle accelerators. The largest is the Large Hadron Collider, or the LHC for short. At the LHC, we collide protons at an unprecedented center of mass energy of 13.6 tera electron volts. There are 4 principal experiments at the LHC. ATLAS and CMS are the 2 general-purpose detectors, while ALICE and LHC-B are specialized experiments. At the University of Oregon, we work on the largest detector, the ATLAS experiment.
We perform collision experiments in order to understand the fundamental building blocks of nature by creating them at our laboratory. The key part here is probably the most famous equation in all of physics, the Albert Einstein's equation E = mc squared.
This essentially means that mass and energy are 2 sides of the same coin. They can be transformed into each other, and that is precisely the idea of the collision experiment.
We give the protons an enormous amount of energy by accelerating them. Then, in the moment of collision, all of this energy is suddenly freed, and we can create new masses, that is, new particles.
Crucially, these particles may not have been part of the proton beforehand. They may be particles that are much heavier than the proton itself, and they may be particles that have never been observed before on this planet. In order to accelerate protons, we need a series of accelerators.
The CERN proton acceleration chain starts from an inconspicuous bottle of hydrogen gas just like this one. All we have to do is strip away the electron in a machine called the duoplasmatron, and we're left with bare protons. For each fill of the LHC, we only need a few nanograms of hydrogen gas. So a bottle like this actually lasts CERN centuries. Next, we form bunches of these protons and then send them to the first accelerator called the linear accelerator right behind me.
This is the first in a sequence of accelerators. This is the linear accelerator, which accelerates the protons coming from the hydrogen bubble to more than half the speed of light.
Inside the accelerator are a series of radio frequency cavities in which a standing electromagnetic wave can be induced. If the field switch is timed perfectly, the protons get a push forward and are accelerated. This concept is true also for other CERN accelerators, including the LHC.
Next, the protons undergo a series of accelerators of ever-increasing size. From the linear accelerator, they are injected into the booster, which accumulates them in 4 separate, superimposed rings and accelerates them to an energy of 2 giga-electron-volts. Next in line is the proton synchrotron, which started its operation in 1959. It increases the energy to about 26 giga-electron-volts, or more than 99% the speed of light. The 7-kilometer-long superproton synchrotron then takes the protons from the proton synchrotron and accelerates them to 450 giga-electron-volts before the protons then enter the 27-kilometer-long Large Hadron Collider in 2 separate beams that can be made to collide. The LHC accelerates each beam to an energy of 6.8 tera electron-volts.
To make the collisions useful to us data analysts, we need a way to capture and record them. To this end, the ATLAS detector is essentially a giant camera with 100 million pixels and takes a snapshot of the collision. We use the information from the snapshot to reconstruct the collision, which can then tell us what particles were most likely created in that collision. But how does the ATLAS detector actually work? Let's go down and find out.
The ATLAS detector is located at one of the 8 access points to the LHC ring. In order to get to it, one has to go down one of the 2 main access shafts. For this, a dosimeter scan and an iris scan is required to get through the personal access doors. Visitors can be comfortably helped through the material access. Getting ready with our safety gear, which means helmets and safety shoes, we can then enter the lift to go down all the way to the level of the Large Hadron Collider, which at this point in the ring corresponds to about 82 meters below ground. In case of an emergency, this is one of the few places in the world where you should actually use the elevator and not the stairs. That's because the elevator room is under higher pressure that would push out any potential smoke. In here we see the service caverns, which house crucial detector, electronics, parts of the trigger system, and everything that's needed to keep ATLAS running. Finally, we step out into the ATLAS cavern and look up at the imposing detector. This feels like stepping into a cathedral of science.
ATLAS is 46 meters long and has a diameter of 25 meters. The cavern it resides in is 10 stories high, and 300 metric tons of rock had to be removed. The build started in 1997 and went on to about 2003. Visitors to ATLAS mainly see the muon spectrometer, the outer layers of the detector.
Every piece of ATLAS was built by different institutions across the globe and shipped to CERN. Like a ship in a bottle, it was put together piece by piece in a cavern around 100 meters underground. Every part had to be lowered through the access shaft, with the biggest part being the ginormous toroid magnet coils, which had to go first to form the frame of ATLAS.
What do we see here?
What do we see here? Here we're at the side of ATLAS. There's the big wheel and the new small wheel and the end cap toroid. So this is where muons will pass through the rest of the detector and come out here, and through the magnetic field get bent, so we can tell the energy of the muons coming through. What you are looking at here is the newest addition to ATLAS, the new small wheel. Part of the muon system, it replaces the old small wheel. The old small wheel has been in use since 2008, and we are hoping to get better performance out of this new detector system.
The new small wheels are, however, not the only detectors that need replacement. Working in very harsh radiation conditions, the detector needs to be continuously maintained, and some detector elements need to be exchanged in order to keep them functioning at their highest possible efficiency. Here we see some workers maintaining the thin gap chambers, which are also part of the muon system.
ATLAS is in fact not just one detector. It is a collection of detectors that surround the primary interaction point, the point where the protons collide, like layers of an onion. The first detector that particles produced in collisions have to traverse is called the inner detector, or tracking chambers. Tracking chambers essentially work like the CCD chip in a camera. You have, for example, pixels that can be ionized by a charged particle traveling through them. Since these particles are all highly energetic, they are not stopped by a single layer of detectors, so we can put multiple layers on top of each other. If now a charged particle passes through, we might see a pixel here, 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 and here, so we know this is the track of the charged particle.
After the inner detector comes the calorimeters, where we try and contain the particles and have them deposit all of their energy within these. First is the electromagnetic calorimeter, where charged particles, like protons or electrons, will pass through and lose more of their energy as they pass through the liquid argon gas, ionizing the gas, and we can read out their energy. After the electromagnetic calorimeter is the hadronic calorimeter, or tile calorimeter we hear also. The tile calorimeter is where we have the hadrons will hadronize, the quarks will keep splitting and depositing more and more energy, and hopefully we contain the hadrons within this calorimeter.
Most particles are stopped in the calorimeters, but not all of them. Muons, for example, are particles that interact very weakly with matter, and they can therefore not be stopped in the calorimeter. Yet we want to do physics with them. How can we do this? In fact, we have constructed an entire subsystem just dedicated to this one particle. So everything that's blue now in this detector is just dedicated to the muon. They work similar to the inner detector. Muon go through, ionize some detector element, and we can deduce that there has been a muon. The muons are then leaving the detector and are lost into the surrounding rock of the cavern. There's another particle that we cannot stop in the calorimeters. This particle is the neutrino. Well, there's in fact 3 of them. Doesn't matter to Atlas, we can see neither of them. Neutrinos interact extremely weakly with matter. In fact, for most neutrinos, the entire Earth is transparent. Yet we can produce them in our collisions. So how can we use them for physics if we cannot see them? Well, indirectly. We know more or less exactly what went into a collision. So if after a collision has happened, we sum up everything we see in the detector, and that doesn't sum up again to the same that we put into it, then we have missed something. And what we've missed, that's the neutrino. Or new physics. Distinguishing those two is the main reason we have a job.
So if all the particles pass through the detector and leave energy, how can we identify what the particle is and its mass is as well? Well, one way is charged particles will bend through a magnetic field. So Atlas has a series of magnets, highlighted here in blue, where if the particle passes through, you can tell how much energy it deposits and how much it is bended by the magnetic field. And using this information, we can tell if it was a muon and how much energy it has, or maybe electrons as well. Therefore, Atlas is designed to do 3 things: track particles, identify them, and identify their fundamental physical characteristics.
Which system have you been working with in the past?
I have been working with the inner tracking system that is in the very center of Atlas. It tracks the charged particles' trajectories in the magnetic field based on which we can calculate their momentum and charge.
Not all subdetectors serve the same purpose. Here, for example, we can see 2 of Atlas's big wheels made out of different detector technology. On the left-hand side, in its golden color, we see the big wheel made out of thin gap chambers. The right-hand side, a big wheel made out of monitor drift tubes. The main difference here is that the monitor drift tubes have a very good spatial resolution, but on the other hand, because they rely on long drift times, have a very poor timing resolution. They are thus used for the accurate tracking of muons. The thin gap chambers, on the other hand, have excellent timing resolution and can give a very fast feedback. They are therefore used for triggering on muons.
Thank you.
So the 2 sides of Atlas are called the A and the C side. Legend has it that they're named after the 2 most important points in an Atlas physicist's life. The A side is pointing towards the airport, the C side is pointing towards Charlie's pub.
To read out the more than 100 million electronic channels, a huge number of cables is required. If you were to lay out all the cables inside Atlas end to end, They would stretch more than 3,000 kilometers, more than from Eugene to Chicago.
Atlas is a fantastic machine, and it's even more amazing when you come to see it. It is huge, as you may have seen, and it's a great honor to be part of the team that works, builds, maintains, and analyzes the data.
What is your favorite subsystem of Atlas?
My favorite subsystem, I would say, is the Muir system, on which I have worked a lot, and I think it's the most of the part you can see.
Daniela, what is your favorite Atlas anecdote?
My favorite Atlas anecdote is that we have tools in our Atlas simulation that got lost in Atlas and are just included within our simulation tool platform.
And that's because the simulation needs to be so precise?
The simulation needs to be as precise as possible, and it was also easier to include it in the simulation and account for it than just trying to retrieve it, because you can't reach them anymore in these specific places.
The cover is actually at an angle because the whole LHC plane is tilted by 2 degrees because of the geological situation the tunnel was dug in.
When you work at CERN, it's fantastic because you get to work with people from all over the world. I think that's what fascinates me the most.
What is your favorite subsystem?
I would say the trigger, because it decides, it filters on the raw data that are recorded by Atlas. And also that's what I worked on my 3rd year of being a member at Atlas.
Well, Atlas is pretty impressive as it is, but my favorite fact is that it weighs about the same weight as the Eiffel Tower.
Do you know how heavy the Eiffel Tower is?
It's about 7,000 tons.
That is a lot.
That is a lot indeed.
If one were to wrap Atlas and threw it into the sea, it would float.
It would actually float because the volume is very big. So we're speaking about a machine which is 44 meters long and about 24 meters tall.
All in all, Atlas is like a 100 megapixel 3D digital camera that takes pictures of every single collision. All the individual sub-detectors, the cryogenics and the vacuum systems need to be monitored continuously. All of this can only be done from a control room which is located 100 meters above our heads on the surface.
My name is Annie. I'm a graduate student at University of Oregon. Welcome to the Atlas control room. This is where you get to monitor data taking of Atlas as well as the sub-detector performance. As a shifter in the control room, you'll be working closely with everyone in the room as well as experts outside of the control room. And the goal here is to make sure that Atlas is running smoothly with good quality data recorded. For me, working in the control room is the coolest part of being at CERN, because not only you get to learn so much about the Large Hadron Collider, also being a member of such a big scientific collaboration, you get to work with and get to know so many people from around the world that are all outside of your home institution.
When the LHC is operating, collisions inside Atlas happen every 25 nanoseconds, or 40 million times a second. This corresponds to roughly 100 terabytes of data per second. We simply cannot use or store this much information, and much of it is not interesting physics. This is because the particles we are looking for happen in only the rarest of events.
And most of the time, it's that the protons collide like this. We're really interested when they're colliding head-on. For this purpose, we have a trigger system that works in 2 levels. The level 1 trigger is purely hardware-based. It reads out the detector information and then within 2.5 microseconds makes a decision whether what we have just recorded is interesting or not. If not, the event information is discarded. If yes, The information is sent to a computing farm that has about 100,000 CPUs that then partially reconstructs the event information to make a refined decision. Was there really something interesting in that event or not? If not, again, the event is discarded. This way, we throw away about 99.995% of our collisions right away. They never get saved. The remaining 1 to 2,000 collisions every second that we do save, however, still amounts to about 100 petabytes of data at the end of a year.
In the next few years, the LHC will be upgraded to have even more intense proton beams. This will necessitate upgrades to Atlas as well. I personally work on the trigger upgrades. I'm currently creating algorithms that will run on hardware, and these algorithms have to be more and more complicated and more efficient to deal with these higher intense collisions.
Hi, my name is Kahan. I am a graduate student working at the University of Oregon Atlas Group. So back when we built the LHC, we expected to discover the Higgs boson, and we did in 2012, which was so far the biggest discovery in this century. We also expected to see more. What we really expected to see back then was supersymmetry. However, we've been looking for it for years and we haven't found anything yet. Another interesting thing that we care about is the observation evidence of the existence of dark matter and dark energy. It turns out everything we've discovered at LHC and before LHC only makes up 5% of the energy content of the universe. And that's called the Standard Model. And the remaining 95% of the energy content of the universe is what we call dark matter and dark energy. So scientists like us now are thinking about using the Large Hadron Collider to create experimental signatures to help us find the remaining 95%, as well as other motivated theories like supersymmetry. What we also do at the LHC is we want to measure the Standard Model as precisely as possible. Any deviation we see from the experimental observation of the Standard Model and theoretical prediction, any tiny deviation will show us that new physics must exist.
Is this an inconvenient time to ask you what your favorite part about physics is?
My favorite part is the teamwork. I would say I need a new teammate.
Go Ducks!
It's pretty strong to me because the
Could you recommend joining Atlas to students?
Yeah, I would definitely recommend.
We have a great time.
Can you recommend joining our group to students? So, have we made our case? I think so.
I think so.
Awesome.
Atlas and the LHC will continue to run up until about 2040, so there's plenty of opportunity for you to get involved. That's the end of our little visit to Atlas and CERN. I hope you enjoyed it, learned something, and we really hope to see you here soon. Is that the end of the video?
Yeah, finally.
Wow, do physics again.